Hess's law uses the idea of the law of conservation of energy to basically state that adding and subtracting chemical reactions, when you're looking at their delta H's, well, you can also add and subtract the delta H's algebraically. And so what that means in an application sense is that we can have an equation 1 and an equation 2 with their associated delta H's, and using this information we can come to a conclusion on what the delta H of a third reaction is. Now, in practice, what Hess's law looks like is recognizing patterns. Basically, you're looking at an equation and seeing, well, are there any similarities between equation 1 and 2, and how can I use those and manipulate those to my benefit? Now, what we see in our final equation here is we have 3a, and actually I should probably add a 2b to this side. If we look at our final equation here, what we have is 3a, 2b, and 5d. And if we look at our first equation here, well, there we have it, 3a and 2b. And in the second equation, we also have 5d. But there's this one little problem. We have this c, this intermediate state, if you will, in between the two. And if you add these two equations together, what you end up getting, this kind of mixed equation between 1 and 2, you end up getting the equation 3a plus 2b plus c, because we're taking it up from this equation, gives us c, because we're taking it down from this equation, plus 5d. And Hess's law tells us that since we've added these two equations together, we can also take the sum of their delta H's. So in this case, delta H equals positive 90 plus negative 60, which gives us positive 30 kilojoules. Now, we're not quite at the step where we have the delta H of the final one, and those of you who are perhaps quicker have probably already realized what we need to do. But basically, since we have C here and C here, we can just cancel the two out, and we get 3a plus 2b gives us 5d. And we, of course, we have the 30 kilojoules, since we've already calculated that. And thus, we have what we want, 30 kilojoules as our final answer, because this is the exact same equation as we need up here. Now, looking at a bit of a tougher problem, here we see that our final equation wants us to have 3 hydrogen molecules, 1 O3, and 3 water vapor molecules. And if we look at the equations up here, we see, oh, here we go. We have 2 water molecules here, we have 2 hydrogens here, and we have O2 here and O2 here. And we have, or rather, we have O3 right here. So the first thing that we're going to want to do is we want O3, this O3 right here, to be on the other side of the equation, or the other side of the line. If we think of all of these arrows as sort of being a dividing line between reactants and products, we want that O3 to be on the other side. So what we do is we just flip it. We say the reverse reaction, 2O3 gas gives us 3O2 gas. Now be careful, because when you flip the reaction, you also have to flip the enthalpy, because now it is no longer going from reactants to products, but rather from products to reactants, and thus you flip the delta H. And so now instead of positive 284.6, you get negative 284.6. However, we're still not quite done, because the coefficients of our hydrogen molecule and of our water molecules are not quite the same. So what we end up having to do is doing a little bit more of this kind of manipulation or mental gymnastics in our head. So what we end up saying is we look to our coefficients and say, if we multiply equation 1 by 3, we get 6 here, 3 here, and 6 here. And if we multiply this equation, I'll label this as 3 and the middle one is 2. If we multiply this equation by 2, we get 2H, 6H, 2O3, and 6H2O. And if we look at our comparison here, well, that's exactly what we want. We want the sixes match up here. The sixes match up here. And it is exactly what we want. So we bring down equation number 1 and we write 6H2 gas plus 3O2 gas gives us 6H2O gas. And in keeping with this algebraic motif, since we've multiplied this by 3, we also have to multiply the delta H by 3. So if you multiply the delta H by 3, you get 483.6 times 3, which is equal to positive, or rather negative, 1,450.8 kilojoules. So now that we have these two equations, we can kind of see where this is sort of leading us, because if we add these two equations together, what we end up getting is 6H2 gas plus 3O2 gas plus 2O3 gas gives us 3O2 gas plus 6H2O, with the delta H being simply the addition of these two negative numbers. And if we add the two negative numbers together, we end up getting 1,735.4 kilojoules. And this should be negative. So, as you can see here, we have two like terms, the 3O2 here and the 3O2 here. So, obviously, we just go ahead and we cancel them. And we end up getting 6H2 gas plus 2O3 gas, which gives us 6H2O. And these two are also in gas. And our delta H remains the same because we haven't changed any of the products or the reactants. We simply cut out an intermediary in the reaction. Now, if we look at the coefficients of this reaction and we look at the coefficients of our third reaction, we haven't quite gotten there yet. In order to achieve the 3 to 1 to 3 ratio, we need to divide the coefficients of this reaction by 2. So we go ahead and do that, and we get 3H2 gas plus O2 3, or 2, gives us 3H2O gas. And of course, keeping with the theme, we also divide the delta H by 2. And that gives us an answer of negative 867.7, which, if we look at the original answer, if we look at the original question, is exactly the answer that we want.